Imagine a tall, slender column supporting a heavy load. As the load increases, the column may suddenly bend sideways. This phenomenon is called buckling. Buckling is a stability failure, not a material strength failure. Buckling occurs when a column becomes unstable under compressive stress. It's like trying to balance a spaghetti noodle on end. It's prone to bending. The taller and thinner the column, the more susceptible it is to buckling. Understanding buckling is crucial in structural engineering. It helps engineers design safe and efficient structures that can withstand compressive loads without collapsing. Buckling analysis is essential for predicting the maximum load a column can carry before it buckles. This analysis considers factors like the column's material, length, cross-section, and end conditions. Why is this important? Because buckling can lead to catastrophic structural failures. Imagine a bridge collapsing because its support columns buckle under the weight of traffic. By understanding buckling behavior, engineers can determine the appropriate size and shape of columns to prevent buckling. This ensures the safety and stability of structures. Buckling analysis is crucial in various engineering applications. Buildings, bridges, aircraft, and spacecraft all rely on columns to support loads. In skyscrapers, columns provide vertical support, transferring the building's weight to the foundation. Buckling analysis ensures these columns can withstand the immense compressive forces. Bridges also rely on columns for support. These columns must resist buckling under the weight of the bridge deck and traffic. Aircraft wings, which act like cantilevered beams, are also susceptible to buckling. The way a column is connected at its ends significantly affects its buckling behavior. These connections, called end conditions, determine how freely the column can rotate and displace at its ends. Common end conditions include fixed, pinned, and free. A fixed end prevents both rotation and displacement, while a pinned end allows rotation but restricts displacement. A free end allows both rotation and displacement. Fixed ends provide the most restraint, increasing the column's resistance to buckling. Free ends offer the least restraint, making the column more susceptible to buckling at lower loads. Section 5. Euler's theory predicting buckling. In the 18th century, mathematician Leonhard Euler developed a formula to predict the critical buckling load of a slender column. This formula, known as Euler's formula, revolutionized structural engineering. Euler's formula considers the column's material properties like Young's modulus, length, cross-sectional shape, and end conditions. It provides a theoretical estimate of the load at which buckling will occur. While Euler's formula provides a valuable starting point, it's essential to remember that it's a theoretical model. Real-world conditions, such as imperfections in the column, can affect buckling behavior. Section 6. Ensuring structural safety. Engineers use a safety factor to account for uncertainties in materials, loads, and construction. The safety factor ensures that the actual load on a column is significantly lower than its theoretical buckling load. By applying a safety factor, engineers create a margin of safety, reducing the risk of buckling failure. This factor considers potential variations in material properties, unexpected loads, and construction tolerances. The choice of safety factor depends on the specific application and the level of risk involved. Structures with higher consequences of failure, such as bridges and aircraft, require larger safety factors. Section 7. Limitations and further considerations. While Euler's theory provides a valuable tool for understanding buckling, it has limitations. It assumes perfectly straight, homogeneous columns, which is rarely the case in reality. Imperfections in the column's shape, material properties, or loading can significantly affect buckling behavior. In such cases, more advanced analysis methods, such as finite element analysis, are necessary. Furthermore, Euler's theory only applies to elastic buckling, where the column returns to its original shape after the load is removed. If the load exceeds a certain limit, the column may experience inelastic buckling, leading to permanent deformation. Section 8. Conclusion. Buckling and structural integrity. Understanding column buckling is paramount for ensuring the safety and stability of structures. From skyscrapers to spacecraft, Engineers rely on buckling analysis to design columns that can withstand compressive loads without collapsing. Euler's theory provides a fundamental understanding of buckling behavior, while modern analysis methods account for real-world complexities. By considering buckling phenomena, engineers create resilient structures that shape our built environment. As we continue to push the boundaries of engineering, understanding and mitigating buckling risks will remain crucial for building a safer and more sustainable future.